later, Josh and I were just working this out, and I'm like, you know what? Why don't I just live stream this? So that's why I'm doing this. If you want to look at it, this will have all the pictures for you, and you can just see it worked out, and I'll put the link in the solution or something. I don't know. Okay, so we have a situation here where we had two capacitors. This is a capacitor C, and it was charged up with a battery so that it had charge EC. Over here, I had a different capacitor that was charged up with a different battery. Okay, and so it has charge 3 EC. So whatever. Somehow we got these two capacitors and they were both charged up. I'm going to connect them plus plate to plus plate, and then I'm going to close this switch. So when I close this switch, some charges might change here. The idea is an electron might leave this plate and go over to here. If it does that, it would appear as if one of the plus charges moved this way, but in reality, it's just the electrons moving that way. Similarly, I could have some electrons moving between these two plates, but they can't jump the gap. We're assuming the voltage is small enough that they don't jump the gap. So the electrons are all stuck on this side. So if I start out with 12 minus signs, let's say, I should end up with 12 minus signs and they might redistribute. Likewise, there'd be 12 plus signs and they might redistribute via the electrons moving around. All right, so we know the charges might change, whatever. At the end of the problem, though, I do know once this reaches equilibrium, if I go all the way around this loop, these two have to have the same change in voltage. So if this one goes up by 3 volts, that one would go down by 3 volts. So they have to have the same size delta V, otherwise energy would not be conserved. Okay? So that's what allows us to say delta V1 prime after they reach equilibrium is equal to delta V2 prime, right? Next, we have, I know Q equals delta VC. So I know that Q equals delta VC. So that tells me that delta V is equal to Q over C. So I'm just going to use that information right here. This would be Q1 prime over, I think that one is C. And this one over here would be Q2 prime over 2C, because this one was 2C. We also know, well, just like I said before, the symbols really help me. If I have 3 plus symbols and 9 over here, I know the total is 12. Well, that's a fancy way of saying Q1 plus Q2, that's the total amount of charge, should equal the final amount of charge. Why? Because they're connected plus to plus, and there's no way for the minuses to cancel either of the excess pluses. So that would tell me this. Aha! I know the initial total charge is 4 EC. Why? Because the problem told me that. We are looking at problem 25.19. Sorry, I forgot to write the number. All right. In this case, I know the total initial charge should equal those. Well, look what we've got now. One equation, two equations, two unknowns. We got this thing beat. So quickly, I'll notice that this cancels. That C cancels. Well, actually, let's leave it in because it'll cancel something else anyways, but whatever. Let's leave it in for right now. Okay, sorry about that. So when I plug in this, well, you have to choose one of these to solve for. So maybe what I'll cross multiply by C. That seems easiest. And now I know that Q1 is actually equal to Q2 over 2. And so if you wanted, you could probably reason it out, but I'm just going to use the equations. I'm going to take this value of Q1 and shove it into there. So now I get Q2 prime over 2, right? That's Q1 prime plus Q2 is equal to 4 EC. Once you do that, you're like, okay, well, this is 3 halves. Oh, that's Q2 prime. I'm getting low on the board there. All right. And so out of all this, I think we can figure out this is equal to 8/3 EC. Okay, now I could grab any equation I want, and we say, well, if that's Q2, this one, I know Q1 is half of that. So that tells me that this is 4/3 EC. And finally, we should check. When I add these two together, I get 12/3. Well, that's 4. That was the original. That was our premise. So we see now that most of the charge will just stay put. But this one originally had EC. A tiny amount might move over here. And I believe that would be, let's see. So if 12 is equivalent to 4, each one, okay, so yeah, so this would be 1, 2, 3, 4, and this would end up with 8. And we see that, yeah, that makes sense. This one we said should have twice as much as that one. And so if those pluses are that way, 1, 2, 3, 4, 5, 6, 7, 8, that allows us to see how these redistribute. How do I get the voltage on each one? I could go back and use this equation right here to get the voltage. Now remember, we assumed that the voltage on 1 should equal the voltage on 2 in the final state, not up here when the switch was still open, but in the final state after they've moved around and reached equilibrium. Why? Because that means energy would be conserved for any subsequent charges moving around the loop. So in this case, we could actually plug in, and I think this one, it looks like, if I divide this one had capacitance C, this one should be what, 4/3 of a volt or 4/3 E? Is that right, Josh? I think so.
Looks right.
So delta V1 prime, I just divided by Q. So this one divided by C, this one was C. So it looks like this would be 4/3 E. And we could check it. So we could check it by going over here. When this one's divided by 2, we should get the same. We do. And we see that our two physical principles, charge is conserved and energy is conserved, are found to be valid if we did this math this way. And so that's a good sign this is right. And so that helps us figure out these charges and such. Josh, was that kind of what you were wondering about, or no, or did I get
Yeah,
it?
I was just missing the step where you like used the two systems of equations to find the total voltage by like
Yeah.
combining and solving for the charge.
Usually I do this in class, and I forgot to today because we got distracted with the simulation. I forgot to go back and do it. So I'm going to stop the live stream now.